Hi everyone and welcome to this talk. My name is Will Santos and I'm a PhD student of electrical engineering and a member of the Digital Systems Laboratory at the Federal University of Brazil in Salvador, Brazil. Today I'm going to talk about the dynamic response prediction of B-state emission of quantum dot lasers based on extreme learning machine. The co-authors are Eduardo Simas Filho, professor at the Federal University of Bahia, and Jorge Terra, professor of the Federal University of Ceará. This talk is the scope of the 21st International Conference on Numerical Simulation of Optical Electronic Devices. Let's begin with the introduction. The object of the study is the quantum dot laser, an important class of semiconductor with distinct properties such as the sharp optical transitions, the low threshold current, the high output power, the large modulation bandwidth. It has some application in several areas like medicine, telecommunication, optical instrumentation, and so on. And most of its interest comes from the carrier dynamics, which give rise to the dual-state emission (DSE) at certain operational conditions. The DSE consists of the optical power emission in two spectral regions, one around the ground state, the GS, and the other one around the first excited state, ES. That is useful for applications requiring wide emission spectrum. So in this work, we discuss the issue of DSE in time domain, but from the perspective of nonlinear regression based on artificial neural network (ANN), using that case the extreme learning machine (ELM), the multilayer perception (MLP), and the echo-state network ESN and LLM hybrid model. The model can optimally filter the switch-on transient of KDL total optical power into the one power corresponding to the spectrum region around the GS and the other one around the first ES, as illustrated in the diagram on the side. It can help to develop the electronics of low-resolution optical filters in those applications in which optical spectrum analyzer is not a choice for cost issues and only one power meter are available. In other words, our research proposes a cheaper alternative to optical filtering using ANN. To get an idea of the KDI characteristic, here we have a quick operation illustrating the figure. The figure illustrates four different types of semiconductors, showing their structural arrangement and their density of states. The first one, the bulk, which are the semiconductors with freely moving carriers, not showing any quantum confinement, so their density of the states is continuous, like we can see at the bottom left of the figure. The second one is the quantum wells. They have restriction in one dimension, so that's changing the density of states. The third one is the quantum wires. They have two restrictions. And the last one is the quantum dots, illustrated in the last column. They have a limitation in the three special dimensions, showing a density of states centered on a few wavelengths. In the case of the study, it's just in two, in the ground state and the excited states. And so you can see here the dual state emission, the object of the work.
Here we can see the diagrams of three different models of AAN. The first, the MLP, is composed of an input layer, an output layer in the intermediate layer, where the output of one neuron is the input of the neuron in the next layer. A popular method to train the synaptic weights is the error backpropagation algorithm, which basically has two phases. In the first one, the synaptic weights are fixed and the input propagates through the network. After that, the backpropagation happens. The resulting errors signal is propagated through the network, but this time the propagation is carried backwards, resulting in successive adjustments in the synaptic weights. The second one is the ESN, is a recurrent ANN which only change the output weights in the learning process, while the other weights remain constant. The figure shows the dynamic of ESN with its three layers: the input, the output, and the dynamic reservoir, where, unlike MLP, the output of the dynamic reservoir neuron can be an input of another neuron in the same layer, like this figure shows. And differently, ELM is a learning technique from a single hidden layer feed-forward neural network that randomly chooses the hidden nodes and analytically determines the output weights. And additionally, in this study, we use a hybrid model ESN-LLM where it has the objective to improve the performance of ESN without losing its main advantages. The model has a ELM as output of ESN, create a model with simple supervised training and based only on the linear combining of the ELM as illustration. About the methodology applied in this work, and more specific about the measurements, they were made a few years ago by the Semiconductor Optics Group of the Technical University of Darmstadt, Germany. The experiment basically consists in the injection direct current into the KDL, controlling its operation temperature with a specific controller. The KDL optical power passes through optical isolation with the aim of allowing the emitted power to travel in only one direction, and then an interference filter to narrow the spectral band, where it will later be detected by the optical power meter and sampled by a fast photodetector. Thus, we can see the main characteristic of the experimental data in these four graphs. In a graph, we have an axis representing the output optical power, in the other, the injection current, which increased by 1 milliamperes per experiment, and in the third is the time since the activation of the KDL. The upper graphics are relative to the optical power of the ground and the excited states, with the operation temperature of 20 degrees Celsius. In the lower figures, we can see the changing behavior of the both power with operational temperature of 40 degrees. So we can see that with high temperatures, the excited states start to emit more, which implies the reduction of the power emitted by the ground states until it is zero, as occurs at temperature around 50 degrees Celsius. In other words, the proposed model must be able to detect this change in the behavior of the KDL.
Here we can see the diagram of the proposed model with the AN inputs considered as the injection current, operation temperature, time, and KDL total optical power at instance n and its k delayed values. The ANN is responsible for predicting the system, playing the role of a nonlinear function. As an output of this, we have the power of the ground in the excited state, that is the optical filtering performed by the model. Below we have the resulting equation of the model. In the case of the model used, we have general parameters which were used in all regarding of ANN. In this case, there was as follows. All data were normalized to minimize distortion in the prediction of neural network. The data training and data test is shared 70% of training and 30% of testing. So the training was supervised. In other words, the data used for the training were pre-selected to ensure that the AN used the different behaviors of the laser in this phase. In the quantum of the delayed input power were determined using a partial autocorrelation function. Thus, the maximum amount of the delayed power to be used was selected. In this case, was 5. In addition to the delayed power with the highest correlation, negative or positive, were selected, which resulted in the discard of the fourth delayed power. And in the other side, we have the specific model parameters. In the case of ELM, we use the sinusoidal function to activate the weights and the number of the high nodes varying from 2 to 1000. With the MLP model, we varied the number of neurons from 2 to 50 due to the high computational cost for training in relation to the others, and the level marked by training function. In the ESN-LM hybrid model, we varied the size of the dynamic reservoir from 4 to 400 neurons. Additionally, in order to validate the proposed model, two wisely used performance parameters were chosen: the root mean square error and the mean absolute percentage error, and their respective equations. Here are our results of each configuration of the model as explained before. The best result of the model using ELM and the best result of our model was obtained with 2 delayed input power and 737 hard nodes. This configuration resulted in an RMSE of 2.89 and a map of 0.54%. So we can also see the inverse proportionality relationship in general between the amount of the delayed input power and the number of hard nodes. In other words, in this case, when the number of input is increased, the degree of the complex of the model is reduced, thus requiring less hard nodes to predict the nonlinear behavior of the system. This feature can be used in the future deployment of this model in hardware. In contrast, the best result obtained by the ESN-LM hybrid model was using just one delayed input power and just 144 neurons in the dynamic reservoir. However, the error obtained are approximately double that presented by ELM with RMSE of 5.56 and a map of 1.02%. And with a much smaller number of neurons than the other two models, with only 44, the MLP had its best result with a RMSE of 8.44 and a map of 1.32%, a error much higher than the other one. And here, the graphic shows the model results for a current of 123 mA with an operation temperature of 20 degrees Celsius in the scenario A, and the result with a current of 140 mA with an operation temperature of 40 degrees Celsius in scenario B. On the x-axis, you see the time in nanoseconds going from the 36.5 nanoseconds to 41 nanoseconds, and on the y-axis you can see the unfiltered optical power with their values normalized. These results were obtained by the best performance model, so that means use the ELM model as we showed in the table before. The figure shows the unfiltered KDL total power, which was mentioned in the experiment, and one of the model inputs in gray, the ground state power, which the experimental one is in red and the simulated one is in black dots, and the excited state power, which the experimental one is in blue and the simulated one is in dotted lines. Thus, we can see graphically verify the low error obtained in the model and presented in the previous table. This happened in the both scenarios, even having power curves with different characteristics due to the different operation temperature. So the conclusion are, the alternative of filtering the KDL optical power from any model is promising, with ELM, MLP, and ESN ELM very low prediction errors. As future works, we will investigate a case of high spectral resolution, at least in continuous wave operation, check the ability of the inference machine to predict different laser lines around the GS and ES. And thank you for your attention, and I will hoping to help you to understand more about my study.